Hi, today's topic is calorimetry and materials and heat. As we recall, heat is the energy that is transferred from one object to another due solely to a difference of temperature. So that's heat. So what we will talk about are two big ideas. One of them is heat capacity. And if you need to stop the video, I've got it written down here. It's not pretty or typed, but it's here. The heat capacity is the amount of energy needed to raise the temperature of a material. The amount of energy by 1 degree. By 1 degree Kelvin. So that's my heat capacity. Kelvin, I'm going to make better color there. Needed to raise the, okay, so I'm going to try and make, oh, I didn't even make it that small. The specific heat, on the other hand, and we give it its own little symbol here. We give it the little letter C. We use that a lot. And it is the amount of energy needed to raise the temperature of 1 kilogram of that material by 1 degree Kelvin. That is the definition of specific heat, and different materials will have different specific heats. The equation that we will be using overall is this one right here, and it's Q, that's the heat, and that's the mass of the object times its specific heat times its change of temperature. So what we have is our specific heat and change of temperature and the mass, and there's the heat. A couple that you might want to write down in your notes, that the specific heat of water, and this is really the only one, the other one there we'll be using in just a minute, is 4,186 joules per kilogram Kelvin. It's a lot of energy. The fact is, water has a very high specific heat. And this is what the specific heat actually means. The higher the number, the more energy it takes to raise the temperature of that material. Also, that's going to be more energy that it takes to lose. So materials with a high specific heat, it takes them a long time to heat up, and then it takes them a long time to cool off. Materials with a low specific heat, like aluminum here, with only 900, less than a fourth of that of water, it takes it almost nothing to heat up, and then it cools off really quickly. So you could think in terms of just how this affects our everyday life. And I'm going out into the ocean, out into the water. We're going to go to the beach. And it's only May. It's a hot day in May. So the water is going to be warm, right? No, because the specific heat of water is so high. That first day in May that it's warm, the water is still going to be really cold because it takes a lot of energy to heat that water. Now, you're going to a nice cool day in September to the beach. The water's still really warm because it hasn't cooled off yet. Same goes at daytime and nighttime. It seems like the water in the pool is often a lot warmer than we think it should be at night. And that night swimming is always fun because the water's warm and it's almost like bath water. Well, it's had all day to heat up. It's sitting there in the sun, warming up. So water works really well that way. On the other hand, something like aluminum, if I've got an aluminum skillet, it's going to heat up really fast. So if I have an aluminum skillet for like a stir fry, it's going to heat up fast. It's going to cool off fast. I like that. So that's going to be easy to use. Something like cast iron has a little bit higher heat capacity. One of the reasons that we use it for things like casseroles and things that require a lot of heat, like roasts, because it takes a little bit longer to warm up. But then it's going to hold on to that heat for a little bit longer. And that's a factor that we use when we're cooking. Okay, so here's some other things that happen. Trying to think. just had a little bit of a brain cramp there. So let's talk a little bit then about, let's do a quick example here. So let's say how much energy is required to heat water from its freezing point to its boiling point. Right. And let's make that 200 or 0.250 kilograms of water, 250 grams of water. That's a cup of water, 250 milliliters of water, or 2 cups. So it's not much, but it's a reasonable amount that you could have when you're cooking. So we're going to take our nice ice water, except it doesn't have ice in it yet, because that's going to be a different lesson. It's just from its freezing point to its melting point. Well, the freezing point of water is 273 Kelvin, or 0 degrees Celsius. And the boiling point of water is 373 Kelvin, or 100 degrees Celsius. Okay. We're going to try and make sure we're sticking with our Celsius here, because or Kelvin here, because we want to stay in SI units. Technically, on some of these, if the units cancel, you can wind up in Celsius, but let's just try to stick with Kelvin here. Okay, so heat Q is going to be MC delta T, and well, we know that the specific heat of water is 4,186, and I've got 0.250 kilograms. My specific heat is 4186. And the change of temperature is 100 Kelvin. The one thing that you can get away with the Celsius and the Kelvin is that delta T in Kelvin is equal to delta T in degrees Celsius, because we're just adding 100 to it, or just adding 273 to it. And so since I'm taking a difference, I don't always need to convert. It's one of those things, though, where as a student, as a teacher, I'm going to encourage you to put the things in Kelvin, simply because we're developing good habits. We want you to be in the habit of thinking of temperature in Kelvin. All right, so here we go. I've got 0.250 Kelvin, or sorry, 0.250 kilograms times 4186 times 100. And I'm going to get quite a bit of energy, and that I'm going to get 104,650 joules, or 105 kilojoules. It's a lot of energy. So that's just the energy to heat up a cup of water. How much does it take? Well, it takes 100,000 joules to do that. All right. So when we talk about changes of heat in the lab situation, and this is one of the most common labs, we don't see huge temperature changes often. We often see very small temperature changes. And one of the things that we'll talk about is calorimetry. Calorimetry is what happens when I've got one object that's hot and I'm going to put it in contact with another object that's cold. Well, the first law of the 0th law of thermodynamics tells me that the energy is going to flow from from the hot object to the cold object. If I leave my hot cup of coffee out on my desk for the entire block, by the end of the block, the coffee is cold. Well, the coffee doesn't get cold by itself. The coffee had more energy than the classroom. So I used my coffee to raise the temperature of the air in the classroom. Just like when I come into the classroom in the morning, my room is a little chilly. After we've put some students in there and they have warmed it up, my room is a little warm in the afternoon. So what we're going to do when this is over, they both have the same temperature. So we're reaching equilibrium. So calorimetry is the reaching of equilibrium from two objects or more with different temperatures. And to do this, what we're going to do is we're going to use conservation of energy, because calorimetry is basically conservation of energy. Okay, so as we would say, energy in equals energy out. So the energy lost by the hot object has to be equal to the energy gained by the cold object. What we will say is that the sum of the heats is 0. So that's the fancy way of writing it. What I like to do is say that the energy of the hot equals the energy of the cold. Easy peasy. So now we know that water takes a lot. So let's suppose I have 40 grams of, I'm going to use aluminum because I know its specific heat is 900. I've got that off because I wrote that up there earlier. Joules per kilogram Kelvin. So there's my specific heat of aluminum. 40 is immersed in 300 grams of water. Oh, I forgot to put the temperature in there. At 395 Kelvin, at 295 Kelvin, what is the temperature at equilibrium? I should be putting something in the problem about an insulated container so that we're not losing energy to the surroundings and all that good stuff. But we will get the big ideas here. So I've got my heat lost, heat gained, and one of them is going to be negative. Doesn't matter which one you make negative because one's going one way and one's going the other way, whatever. So the negative of the heat lost is equal to the heat gained or opposite thereof. I just put the negative on the other side. You can do it whichever way you want. So in this problem, the aluminum is losing the energy because it's coming in contact with something at a lower temperature. So this is going to be the aluminum and this is going to be the water. Okay, cool. So we have that. And so Q is MC delta T of the aluminum. And that's going to be negative Q MC delta T of the water. Well, what I don't have is the delta T. I don't know the final temperature. So I'm going to set those equal to each other. So the mass of the aluminum times the specific heat of the aluminum times the final temperature minus the initial temperature of the aluminum. So that's T initial of aluminum. That's going to be negative mass of the water, specific heat of the water, times T final. Notice that these two T finals are the same because they've reached equilibrium, minus the T, gosh darn it, initial of the water. Heat lost by the hot object equals heat gained by the cold object. Okay, this makes sense. All righty. Now you can have fun with some algebra here. You can just start plugging in numbers. It's up to you. Me, I'm going to distribute because I do not like that negative there. And so I'm going to say that the mass of the aluminum times the specific heat of the aluminum is T final minus T initial of the aluminum is equal to the mass of the water, specific heat of the water, times minus T final. So I switched that out to get rid of my negatives. Whew, makes me much happier. Okay, now you can algebra all you want. You can put it in Desmos at this point for all I care. All you've got to do is go ahead and actually plug in my numbers. So I'm going to say then that I have the mass was 40 grams. I'm not going to change these to kilograms. The reason I'm not going to change them to kilograms is that these are all going to cancel out. Those are all going to cancel out. And so I'm going to have 40 grams. As a matter of fact, I'm even going to put the units in here. Specific heat of aluminum is 900 joules per kilogram Kelvin. My final temperature is my variable. And my initial temperature was 395. And this is now going to be, what, 300 grams. And the specific heat of water is 4186 joules per kilogram Kelvin. And the initial temperature of the water was 295 minus the final, minus the equilibrium. Okay. Ugh. So when I bring those over, and I'm actually going to go ahead and do this, I'm going to put my 300. And the reason I'm doing this is to show you that the units do indeed cancel, because I know I'm a stickler for putting everything in SI units. And here I am not putting anything in SI units. Okay. Bam, bam, those all cancel. My grams cancel. Those cancel. And so I'm now just left with Kelvin. So it didn't matter that I didn't change those units out because they were going to cancel. All right. I'm going to go ahead and grab my calculator here and say that that's going to be 40 times 900 divided by 300, 4186. Make sure I put my parentheses where they belonged, and I get 0.02867, and I kept a couple of digits there, times T final minus 395 is equal to 295 minus T final. I can get rid of that parentheses there. That's cool. And now I can distribute at will. The hardest part about calorimetry, honestly, is the algebra. The concept is easy. Energy lost equals energy gained. We spent half of physics 1 doing that. I had the energy. Where did it go? Aluminum had energy. Where did it go? Oh, it went to the water. Got it. It's just conservation of energy. However, as you've seen, the worst part about calorimetry is the fact that, I've got to do some wonky algebra. If we have more than one object, we just have to add more terms. It doesn't change the physics, it just means more algebra. So I'm going to take this number and multiply it by 395. And so I get 0.02867 times T final minus 11.323 is 295 minus T final. I'm going to add T final to both sides, and this becomes 1.02867 T final. I'm going to add 11 to that, and I get 306.3. Divide. And I get 298 Kelvin. Now, here is what you have to actually think about now. Looking at my answer, there's my equilibrium temperature. We started out at 295 and 395. The final temperature has to be between those two. It violates conservation of energy for them to be anywhere but in between those two. So now let's take a look. 298 is awfully close to 295. Does that make sense? Well, it does, because we had a lot more of the water than we had of the aluminum. And we also have a lot higher specific heat of water than of aluminum. So it makes sense that the final temperature is going to be a lot closer to the temperature of the water than it was of the aluminum. So if in an industrial situation for you future engineers, a good way to cool off a hot piece of metal is to put it in a vat of cold water. A good way to warm up a piece of metal is to put it in a vat of warm water. That's essentially, we do that with food, we boil it. But a good way, if you've got a steaming or a really hot piece of metal that you've been working with, a quick and easy way to cool it off is to put it in cold water, immerse it. It cools off so fast. Okay. That is calorimetry in a nutshell. If you have more objects, suppose I had a piece of aluminum and I had some copper and I put them in together, and I had water, and maybe I mixed some alcohol. We do this with antifreeze to keep it from freezing. And so it doesn't change the physics, it just changes the algebra. What you will be looking at is the fact that you've got heat lost equals heat gained. Don't forget there's a negative sign. As you get used to it, what you wind up doing is making that switch immediately. I will have a tendency to put the hot thing. Where is my heat coming from and where does it go? I just set it up the same way I did gravity potential energy, because that's what this is. We've got potential energies. And then you can set, like I said, set up your algebra. Those of you with fancy calculators and Desmos, the algebra becomes trivial, but we do have to interpret it to make sure that you've set it up correctly. Okay, our next topic of conversation will be calorimetry with phase changes, because that makes life a little different when we actually change phase. And then we'll talk about the heat transfer at the rate of heat transfer and conduction. So those are going to be the topics for the next couple of lessons. And just keep on working on those assignments. We'll see you in class. And remember that we're all in this together.